So we now come to a calculation of dose, absorbed dose and effective dose. Suppose we have a person who has a mass of 70 kilograms. They're sitting near a wooden desk, an office desk, 6 hours a day, 5 days a week, 50 weeks a year. They get some vacation. And let's suppose this desk has 8 kilograms of carbon. These are just complete guesses, but let's suppose it's 8 kilograms of carbon. And some of that carbon will be carbon-14, and let's say that 5% of the emitted radiation is absorbed by the person, and each beta has 0.156 MeVs of energy. We can look up the abundance of carbon-14 is small compared to carbon-12. That should be carbon-12 here. Cut and paste and didn't edit. The abundance of carbon-14, 1.3 times 10 to the minus 12 compared to carbon-12 presence. Let's calculate the absorbed dose and the effective dose. So in doing this, we'll need to determine how much activity there is in the desk, and then 5% of that will reach the person. So that's kind of our scheme. There'll be an energy per beta ray. And the dose, of course, is how many joules of energy per kilogram are absorbed. So those are some of the steps. So one step we need is the mass of the carbon-14 that's in the desk. And we have an abundance, 1.3, 10 to the minus 12, that we can multiply by the 8,000 grams. Grams are a little bit more convenient to work with than kilograms. So 8 kilograms of carbon, 8,000 grams of carbon, and a certain abundance of the carbon-14. So we have 1.04, 10 to the minus 8 grams of carbon-14 in the desk. How many atoms of carbon-14 do we have? So let's calculate the N. We're doing this because our activity is lambda times N. So we're going to see that calculation in just a little bit. We need the number for N. So we can use the fact that we have this mass, 1.04 times 10 to the minus 8 grams, and the fact that 1 mole of carbon-14 is about 14 grams. For our purposes, that's close enough. And then Avogadro's number, 6.02 times 10 to the 23rd atoms per mole. Our moles cancel, our grams cancel, and we find that we have 4.472 times 10 to the 14th atoms of carbon-14 in this desk. So our activity, as we pointed out, our activity is lambda, the decay constant, times the number of nuclei we have. So we're ready to do that calculation. Lambda is always 0.693 on the numerator, and divide by the half-life, 5,730 years. And we have N, 4.472 times 10 to the 14th. So that produces 5.409 times 10 to the 10th decays per year. So you ought to check this on your own calculator, make sure you come up with that number. And then I'm going to choose to go to decays per hour as a unit here. So 1 year, 365.25 days. And then in 1 day, we have 24 hours. So this gives an activity value of 6.17 times 10 to the 6th decays per hour. I did this because we're given data on how many hours the person puts in at the office. 6 hours a day, 5 days a week, 50 weeks a year. So now I have how many decays per hour are in this desk that the person is sitting in front of. So the number of hours of exposure, so I can find the number of decays that happen. The number of hours of exposure We have 6 hours each day the person is at the office. We give them 2 hours to walk around. 5 days for a week. 50 weeks for a year. So they're sitting in front of that desk 1,500 hours per year. It's a desk job. So how many betas are going to be absorbed by the person? Well, we're only going to absorb 5%, so 0.05 of the number of betas that come out of the desk. And we have an activity 6.17 times 10 to the 6 decays per hour. And we have 15 hours per year, 1,500 hours per year. So this person is receiving 4.63 times 10 to the 8th betas per year. Now let's calculate the dose. Our dose is the number of joules absorbed per kilogram. So we have the number of betas that are absorbed. Up in the wording of the problem, we're told the energy value for each beta. So we can combine that information headed towards joules here. So 4.63 times 10 to the 8th betas with 0.156 MeV per beta. And then we want to get to joules. So a conversion factor to bring us to joules from MeV, 1.6 10 to the minus 13 joules per MeV. So I've done the calculation to calculate how many joules of radiation, how many joules that carried by this radiation the person has absorbed. And we're told the person is 70 kilograms. Again, you should pause and do this calculation, see what value you come up with. I have 1.65 10 to the minus 7 joules per kilogram. That would be grays. The gray is 1 joule per 1 kilogram. So our absorbed dose here, 1.65 times 10 to the minus 7 joules per kilogram. If you're using the older unit, the rad, the numbers become 100 times bigger. So 1.65 times 10 to the minus 5 rads. To get the effective dose, we take the absorbed dose times the relative biological effectiveness of the radiation. I've chosen an easy problem because for betas, the RBE value is a 1. So in terms of our effective dose, we can convert the grays directly into sieverts. 1.65 times 10 to the minus 7 sieverts. I had 1.65 times 10 to the minus 7 grays. The sievert is the number of grays times the RBE number, and that's a 1 for the betas. They're not the most dangerous radiation, so a 1 for the RBE. And in terms of REMS, again we take rad times 1, and we'd have 1.65 times 10 to the minus 5 REMS in that older unit. And sometimes we like to go to the milli unit. I'll do that for the REMS. A milli is 10 to the minus 3. So this would be 1.65 times 10 to the minus 2 millirems. It is not a dangerous desk. Hopefully I've not neglected to account for the uranium ore that somebody left in the desk, as I did when I was growing up, and my uncle geologist gave me a sample of uranium. Fortunately, my mother threw it out before too much damage was done. So there's our calculation for dose. We need to somehow get to joules. To get the number of joules, we came up with the number of betas that were absorbed by the person taking into account only 5% emitted by the desk. They go out in all directions. Some of them are stopped inside the wood, and this is a complete guess, this 5% that I'm just throwing in here. But we somehow come up with the joules of radiation absorbed, that energy absorbed, and divide by kilograms. That gives us the dose, and multiply it by RBE to get the effective dose. Keep practicing. Ask your instructor questions.